number 4 on differential form of the first law is a mess. So sorry about that. That I just copied it down from the book and I copied it down all wrong. So let me give you the real problem. I'll fix it on there and let me just go through it because, yeah, that's frustrating. So this is differential form of the first law. Number 4. And it says that you have 1 kilogram of a certain refrigerant 22, and we don't need the table for this, but we do have tables for that refrigerant. And it says that it starts out with a pressure of 0.9 megapascals and a specific internal energy of 232.92 kilojoules per kilogram. And then over a process that takes 20 minutes, it comes to a new, I think it gives a pressure to, but the thing that we're going to need is the specific internal energy at that second state of 276.67 kilojoules per kilogram. Okay, it says it's a rigid tank. And what that means is that the gas can't expand. And so there's not going to be any work done by expansion or contraction of the gas. And it says there's a paddle wheel inside. And that adds energy to the gas through work. So that does work on the gas at a rate of 0.1 kilowatts. And then there's also heat transfer from the refrigerant. And that's happening at a rate of capital K times T, and that's in kilowatts, where that time T is in minutes. And we want to calculate two things. We want to calculate that constant K, and then we want to calculate the heat and the W over this process. Okay. Well, normally, most often, if you see stuff in watts, you're going to end up using the differential form of the first law. But this is one where you're actually doing this over a process with over a finite amount of time. And so we're going to have to integrate these functions for the heat transfer and the energy transferred by work over 20 minutes to come up with a total amount, a total W and a total Q. So we're heading towards this. The change in energy is equal to Q minus W. The change in energy is equal to the change in kinetic energy plus the change in potential energy plus the change in U. And that's equal to Q minus W. Since it's a rigid tank, and it actually says this in the problem, but we're not talking about this thing flying through the air or being raised. So these go away. It says that explicitly in the problem, but normally we're going to be able to assume that if there isn't reason to believe that they change. Calculating the change in U is pretty easy. So the change in U is equal to capital U at the later state minus capital U at the earlier state. And that is 276.67 kilojoules per kilogram times 1 kilogram minus 232.92 kilojoules per kilogram times 1 kilogram. And so we just get a value of positive 43.75 kilojoules. And now let's calculate the work done by the paddle wheel. So first we have to think about the sign. Our system is the refrigerant, but and this paddle wheel is doing work on the system. So is that going to be W, positive W, or a negative W? Negative. And so W dot is equal to negative 0.1. And that's in kilowatts, which we can think of as kilojoules per second. And so the total work is the integral over 20 minutes. We have this in seconds, so we have to integrate this with respect to time in seconds. So we're going to go from 0 to 20 minutes in seconds is 1200 of negative 0.1 dt. And if you do that integration, you just get negative 120. And that's in units of kilojoules. And now the last thing we need is the heat. And so again, let's think about that sign convention. That this sign convention for the first law comes into almost every problem we're going to do. So we're talking about heat being transferred from our system to the surroundings. So is Q dot positive or negative? Negative. And that's equal to negative KT. That's with time in minutes. Um, and this Q dot comes out in kilowatts. So we want to, if we integrate this with respect to time in seconds, we'll come up with kilojoules. So that's what we want. But to do that, we have to express Q dot with time in seconds. And so Q dot is equal to negative KT over 60. With time in seconds. And now we can integrate with respect to time and get energy in kilojoules. So the heat is the integral from 0 to 1200 of negative KT over 60 dt. And that's equal to negative K over 120 T squared, evaluated from 0 to 1200. And if you integrate that, you get negative 12,000 times this constant K that we don't know yet. And that's in kilojoules. But now we have all of these terms for the first law in kilojoules. So now we can put it all together. We have that delta U is equal to Q minus W. Delta U is 43.75, yeah. And that's equal to negative 12,000 times this constant K. And then minus W, and W is negative, so we have double negatives here, negative 120. And so for part A, the first thing we want to do is solve for that constant K. So 12,000 K is equal to 120 minus 43.75. That's 176.25. And so K is equal to 0.0146. What? Yeah, move some of those numbers around. It's like the Price is Right. So wait, 70, now this is right? Okay, yes, I was so close. Thank you. So K is 0.0146. And now for part B, we want to calculate. Oh, it does? So what do you get? 0.00635. Okay, thanks. Okay, so now plug that back in for, well, we already know what the work is. That wasn't dependent on Q. So W is equal to negative 120 kilojoules. Q is equal to negative 12,000 times this, which just gives us back negative 76.25, right? and that's also in kilojoules. Any questions about that? Okay, I'll fix that on the homework sheet for when you have to do it again. Are there any other homework questions? Yep, sure. Do you have the sheet with you? Okay, so air is contained in a piston cylinder and the piston is connected to a spring. The volume goes from, so V1 is 0.003 cubic meters, and V2 is 0.002 cubic meters. So the air is contracting, and the spring force varies linearly with volume we're talking about. That also, by the way, in a piston cylinder system, that's the same as what a spring usually does, varying linearly with length. From a spring force of 900 newtons to a spring force of 0. Okay, so draw a picture of this. We start out in state 1. With a spring force of 900. Okay, draw that in a second. And a big volume. And then in state 2, we have a smaller volume. Here's the air. Here's the air. The force here is, in the second one, state 2 is 900. No, 900 in the first state and 0 in the second state. So so there's a spring like that that's being stretched, and in state 2 it's returned to its resting length. That is the only way that could work, right? The only way that you could have, I mean, you could also have a spring up above that was compressed, and then it goes back down to here, but mathematically it's the same thing. So this is the only way you can configure that. The area of the piston face is 0.018 meters squared, and the atmospheric pressure is 100 kilopascals, or 1 times 10 to the 5th pascals. So first, it asks us to isolate the piston at each state and calculate the pressure in the gas. So if you draw a free body diagram for state 1, that spring is applying a downward force, and the magnitude is 900 newtons. The pressure from the atmosphere, this is the outer pressure, is 1 times 10 to the 5th times the area of that piston, that's 0.018. And then you also have the gas pressure pushing up on the piston. That's the area 0.018 times our unknown pressure P1 for the gas. And so Newton's second law says 0.018 P1 minus 900 minus 1, 2, 3. So that's 1.8. So that's just 18, right? Is that 18 or 180? 1, 3, 4, 5, 1800 is equal to 0. Newton's second law, yeah. Okay, so P is equal to 1 times 10 to the 5th plus what's 900 divided by 0.018? What? Okay, so plus 50,000. So that's 1.5 times 10 to the 5, I think. And then at state 2, I'm calculating the pressure in the air that's inside the cylinder. I added atmospheric just because this is a free body diagram and I'm just using Newton's second law. So to calculate the forces produced by the pressures, you just multiply that by the area, the cross-sectional area of the piston. So you have atmosphere you know, atmospheric pressure is pushing down on the piston. So you have, that's where the atmospheric pressure comes in. It's pushing down on the surface, and it's that times the area of the piston. And then state 2, we have 1 times 10 to the 5th times the area, pushing down, pushing up. We have the unknown pressure times the area, and Newton's second law. This one just says that P2 is the atmospheric pressure. Okay, we want to calculate the work. So we know that the spring force, so that spring force is equal to, we know it's a linear function. You can think of that as, let's write it as m times volume plus b. Okay. I think we're going to come out with that additive constant being 0, but that's the most general linear function of volume. And so we can plug this in at the 2 states. At state 1, we have 900 newtons is equal to 0.03, was it? Yeah, 0.03. 0.003 times m plus b. And at state 2, we have that 0 is equal to 0.002 m plus b. So from this one, you can see b is equal to negative 0.002 m. And then substitute it into the first one. And you get 900 is equal to 0.003 m minus 0.002 m. So 0.001 m. And so m is equal to 900,000. Pressure. Yeah, that would be the same. So it's a little unusual to think of a spring force as a pressure. So I'm not used to doing that, but it would work out fine in this case. The reason it would work out fine is because the cross-sectional area doesn't change as this problem happens. So you could just as well think of this spring, divide the force by the cross-sectional area and you get sort of like a pressure. This is a more usual way to think about it. Okay, so now plug that back in for B. What's 0.002 times 900,000? Okay, so you get 900,000 times volume minus 1800. And now let's think about a general free body diagram. So you have the downward force of 0.018 times 1 times 10 to the fifth. That's from the atmospheric pressure. You have the downward force from the spring. And now we have an expression for that. And we have the upward force of 0.018 P. And so Newton's second law says 0.018 P minus 1800 minus this expression for the spring force. So that's 900,000 V minus 1800. And that's all equal to 0. The 1800s cancel. And you get that 0.018 P is equal to 900,000 V. Now multiply both sides by 0.018. And what do you get for that? Divide by, sorry. Okay, so 5 times 10 to the 7th times the volume. Okay, so it asks specifically, this question asks specifically to calculate the pressure in the gas at states 1 and 2. But it didn't ask specifically for this expression for the pressure as a function of volume. But why did I do that next? What's the benefit of coming up with the pressure as a function of volume? Yeah, because we're heading towards, we're trying to calculate W for the gas. W is the integral of PdV. And so you can't calculate PdV unless you have pressure as a function of volume. So work is equal to 5 times 10 to the 7th times V, dV. And it's integrated from the starting volume of 0.003 to the ending volume of 0.002. And so that is 2.5 times 10 to the 7 V squared, evaluated from 0.003 to 0.002. Can someone calculate that? Negative 125. Okay, so that's a pretty small amount of energy for all that calculating, all those 10 to this. But does it make sense that W comes out negative? Yes, and why? Because the volume's decreasing. Yep. Well, what it says in the problem is the spring force varies linearly from 900 newtons to 0. Excuse me. The only reason that we really care about that spring force is because we needed to calculate pressure as a function of volume for the gas. But we started out with, it said that it was a linear function to get the spring force, and then we used that. Um, that way of thinking about it would work perfectly fine with a piston and a cylinder. People just uh, don't usually talk about like uh, spring forces in terms of pressures. It's just like people aren't used to hearing that, so you might as well get used to doing it the way people are more used to hearing it. Yep. Um, could you have done that? I guess in this case, that would have been true. I would not have immediately, like, it wouldn't have been totally obvious to me that that was true. So, I mean, if that's clear to you, it's sort of the same thing as math proofs, like you've done math classes where you have to do proofs. Like, what does it mean to prove something? Well, if you understand all the steps, basically you're just trying to get to the point where you understand 100% that it works. And if you understand 100% that's how that would have worked out, then that's fine. Just if you don't understand it, then you have to convince yourself. Yeah. Because it's you can pull that outside, and when you integrate v dv, you get v squared over 2. Any other questions about that one? Yeah. Yeah. Oh, really? Huh. I guess it made more sense to me. Um, did it say that in the problem that pressure was a function? Oh, okay. Well, that saves you a little work. Yeah. But whatever. So I guess the answer then is you got to go with what it says in the problem. This problem kind of required one more step of uh, because you're still eventually trying to get to pressure as a function of volume, but it didn't tell you right off the bat what that relationship was. Any other questions about this one? Right. Yep, that's right. And then you just have to, so anytime you're talking about forces, you're going to have to use Newton's second law to go from there to the gas pressure. And then the reason in these you usually need to know the gas pressure is because you're usually going to get W as the integral of PdV. Any other homework questions? Okay, so last time we started talking about interpolation. And the reason that we're going to do that in this class is so we can use the property tables at values that are not uh, mentioned in the property tables. Property tables and interpolation. Um, and we talked about to interpolate a function of one variable, one independent variable, um, our approximation for our f value that we want, I'll call it f of x, and we're going to approximate that as f at the first value of the function that you know, plus in the numerator, the function of the second x value minus the function at the first one, divided by x2 minus x1, and then times delta x, where delta x is equal to x minus x1. I think we did one example for that. So let's do an example where we use the property tables. So at a temperature of 63 degrees Celsius, what are the pressure and the specific internal energy for first saturated water vapor, and second for saturated liquid water? Okay, so what we're talking about here is this is the saturation temperature at whatever pressure we're going to find. At atmospheric pressure, the saturation temperature for water is 100 degrees Celsius. So is this going to be a high or a low pressure compared to atmospheric pressure? When we find this P, it's going to be low, yeah. Anybody have any questions about what we're doing on this? Okay, so I think I have a little part of the table. Do you see one that says lecture or anything? Oh well, we'll just use the full one. Okay, so there, for saturation values, there are two different ways we can look at this information: indexed by temperature or indexed by pressure. Which one do we want in this case? We want temperature because that's what we're given. So we'll go to water. Okay. And we want 63 degrees. So scroll down until you get into that ballpark. And the two closest values that bracket 63 are 60 and 65. So to calculate the pressure, we're going to need the pressure at saturation at 60 degrees and the pressure at saturation at 65. So 0.1994 and 0.2503. So at temperature equals 60 degrees Celsius, the pressure is 0.1994, and that's bar. And for a temperature of 65 degrees, the pressure is 0.2503 bar. And I guess while we have the table out, let's also get the specific internal energy values. So at 60, which one are we doing first, vapor or water? Or vapor or liquid? Okay, so the specific internal energy for vapor at 60 is 2456.6, and that's in kilojoules per kilogram. (2456.6) kilojoules per kilogram. And at 65 degrees, 2463.1 kilojoules per kilogram. Okay, so first we'll do the pressure. So the pressure at a temperature of 63 degrees Celsius. Yep. We're going to approximate that as the pressure at state 1 at the lower temperature plus the later pressure, or the higher temperature pressure, minus the lower temperature pressure. So 0.2503 minus 0.1994 divided by the difference in temperatures. And then times the x value that we want, 63, minus the x1 value of 60, so that's positive 3. And I think you get about 0.22994. So it's in between those two values, closer to the 60 value because we're closer to 60 degrees than 65 degrees. No, we're not. Closer to the 65 degree. And this is in bar. And now do the same thing for the specific internal energy. The internal energy at a temperature of 63 degrees, we're going to approximate that as 2456.6 plus the quantity 2463.1 minus 2456.6 56.6 divided by 65 minus 60 times 3. What do you get for that one? 2460.5. And that's kilojoules per kilogram. And so now, like, if you did a problem where say you knew that this pressure was going to be constant, you were, well, this is saturated, but say you know something about the work or you know something about the heat, you can calculate the big U change in internal energy using this. You can use that to find the change in internal energies and use the first law of thermodynamics with these table values to calculate, you know, whichever one you didn't know, the heat or the work. Okay, so this was for the vapor. The pressure isn't going to change when we switch to saturated liquid. So all we have to calculate for the saturated liquid is the new internal energy. Do you expect the new specific internal energy to be bigger than this or smaller than this? So for the vapor at that same saturation temperature, if you go from, so if you start with a saturated liquid and add energy until it's a saturated vapor, you've added a lot of energy to this material to spread the molecules apart. And so you're always at the same saturation point, you're going to have a lot more energy in the saturated vapor than in the saturated liquid. Like over 1,000 times as much. Okay, so for this one, at a temperature of 60 degrees, from the table, our specific internal energy is, so the saturated liquid yeah, I'm just surprised it's yeah, I guess it's the, okay, so the internal energy, I guess I was thinking of the volume that has that super big difference, but saturated vapor is always going to have a bigger internal energy than the saturated liquid. So for this one, 251.11, and that's kilojoules per kilogram. And at a temperature of 65 degrees Celsius, we're at 272.02 kilojoules per kilogram. And so now our estimate for the internal energy for a temperature at 63 degrees Celsius is 251.11 plus the quantity 272.02 minus 251.11 divided by 65 minus 60 times 3. And what do you get for that? 263.656 kilojoules per kilogram. Any questions about those? Okay, it's a little more tedious, a little more complicated. Interpolate when you're using the compressed liquid or superheated vapor tables. And the reason for that is because each property is a function of two independent variables now. So each one is a function of both temperature and pressure. For the saturated tables, we could choose which one of those we wanted to work with and only work with that one. So this one, we're going to have functions of two independent variables. So what we're talking about is, so linear interpolation of functions of two independent variables. And so the way you're going to always start with this is you'll have a grid of values. We'll have an x1 and an x2, and we'll be looking for, well, and to finish the grid, now we have values like this for the y's. Let's say this is y1, y2. And our function of the two independent variables is a surface over the top like this. Okay. So we're trying to estimate the height out of the page of this surface at some value inside this grid. That doesn't happen, you know, if we're lucky, it falls right on the nodes where our known values from the table of x and y meet. But more often, we're going to be looking for the function value at a point like this. Where this is the x we want, this is the y we want. And so what will be given, you know, we're going to approximate this function at x, y on the grid, knowing f of x1, y2, f of x2, y2, f of x1, y1, and f of x2, y1. We're going to know the function values at these four nodes. and we're going to use that to approximate the function value here. And we're going to do that as a series of 3 1D interpolations. And you can think about this. There are 2 different orders you can think about this, and either one is fine. They won't give the exact same answers, but they'll approximate things equally well. But so what we're going to do is first, we'll approximate so let's say we'll approximate f of x y1 as f of x1 y1 plus f of x2 y1 minus f of x1 y1 divided by x2 minus x1 times delta x, where that delta x is equal to x minus x1. So do you see how that's just, we have this second variable y1 just sort of hanging around for the ride. The only things that are varying are that first variable. And so now, if you ignore the fact that this y1 is here and just plug that in, what you have is an interpolation, a 1D interpolation approximating this function value at x, using the function values at x1 and x2. Just with me on that. Okay. So that's the first one. Then the second one, what do you think the second one's going to be? Yeah, so now we're going to approximate f for x and y2 and do the same thing we did here, except any place that y1 was plugged in the first step, y2 is going to be plugged in the second step. So we have f of x1, y2 plus f of x2, y2 minus f of x1, y2 divided by x2 minus x1 times delta x. And delta x means the same thing it did there. And now that we have those 2 approximations of the function value at the x that we want, what do you think the third step is going to be? Now we're going to interpolate using y1 and y2 to our desired y value. So f at x, y is approximated as f of x, y1 plus f of x, y2 minus f of x, y1 divided by y2 minus y1 times delta y, where delta y is y minus y1. 3 steps. Okay, let's try this. So let's say we want to approximate this function, function of xy, and let's say it's equal to xy squared. At x equals 2, y equals 2, given these four values, and this would be like what you would read out of a table. So let's say we're given that f of 1, 2 is whatever you get there, 4. F of 3, no, that can't be 2. So let's say this is, so the first one we know is f of 1, 3. The second one is f of 3, 3. What's that, 81? Yeah, thanks. And then f of 1, 1 is 1. And f of 3, 1 is 3. Okay, so the first step is we're going to approximate f of 2, 1. Yes. 27. Yep. Thank you. That would have screwed everything up. Thanks. Okay, so the first thing we're going to do is approximate f21. No. Okay, so all the stuff we're given, we have f of 1, 3 is 9. F of 3, 3 is 27. F of 1, 1 is 1. And f of 3, 1 is 3. And the first step is we're going to approximate f at 2, 1 as f of 1, 1 plus f of 3, 1 minus f of 1, 1 divided by 3 minus 1 times the delta x of 1. And so we'll get 2. Any questions about the first step? Then the second step so the second step is we're trying to find f of 2, 3. Why isn't this hiding? So f of 2, 3, that's going to be f of that's going to be f of 1, 3, which was 9, plus f of 3, 3 minus f of 1, 3, which was 27 minus 9, divided by 3 minus 1, times delta x. And so that's 18 minus 2, 9. So we get 18 for this one. And then the last step is we want to approximate the function at 2, 2. So to do that, we're going to take f of 2, 1 plus f of 2, 3 minus f of 2, 1 divided by 3 minus 1 times delta y, and we get a value of so 16 minus 2, 8, 10. Okay, so how does that compare to the real value at 2, 2? That's 4 times 2 is 8. So it's closer than any of the 4 corner values. And we'd get better values if we used a tighter mesh, if our grid of values that we knew were closer to the x and y values that we wanted. Any questions? Yeah. Yeah, that's right. And, so you just want to take the closest values you have that bracket the value that you want. So you need one that's less and one that's more in each dimension. Any other questions? Okay.